our data, if we're looking at experiments 1 and 2, we triple the concentration. Okay, so there is an equation that I will show you that you can use to calculate the order with respect to a given reaction. But there are ways to look at this, look at the data, and determine the order. It takes some practice, but it's totally doable. So let's say that we're looking at our experimental data, and we notice that the concentration is doubled for a given set of data. For one reactant, the other is constant. So we know the concentration is doubled. Now we look at how the rate is affected. If the rate is doubled, then we know that the order with respect to the reactant is 1. We double the concentration, the rate is doubled, the order is 1. Okay? There's a log involved here, and when I show you the equation, I think this will start to make more sense. If we double the concentration of reactant and the rate is quadrupled, the order is 2. So if, let's say, we double the concentration, the rate is quadrupled, the order has to be 2. Does that make sense? Okay. You can do that if you double the concentration of reactant, the rate doesn't change, you know the order is 0. Totally possible. If you double the concentration of reactant, the rate is halved, the order is going to be -1. So typically we see whole number orders, not always, but that's pretty typical. And you can occasionally see a minus a whole number. Okay? So, but you know, if we look, we've got another issue. Yeah.
Will we see orders higher than 2?
It is technically possible to have orders higher than 2, but it's very uncommon. Yeah. In terms of being realistic about what's happening with chemistry, it's very uncommon. Right? This is sort of easy for me to picture, the doubling. So let me show you the equation. Now, I do want to say you will not get this equation on the exam. And I don't believe it's in your textbook. But I like this equation because it sort of simplifies things. Okay. So in order to find an order, with this equation, you can take the log of rate 1 over rate 2 divided by the log of concentration 1 over concentration 2. Okay. So if we're looking at the order with respect to ClO2, M is going to be equal to the log, we'll do rate 2 is 0.00276 over 0.0248. So I'm using this as rate 1, this as rate 2. Over, this is concentration, yikes, concentration 1, concentration 2. It doesn't matter which way you pick it as long as you're consistent. So since I picked the rate from experiment 2 to be 1, I have to make sure I do that for both the rate and the concentration. You can divide these out, take the log, divide the whole thing, and get a value. Okay? And so, you know, I think we end up with what here? so this is m, tripled up at 9, so that's 2. I didn't do the math on that one. Yeah.
Why did you put the .024 on the bottom, like on the top? It says 32. If it's like next to number 2, it
Yeah.
says .00276.
Did I mess up my numbering? So I did the experimental data from this one as 1, and then the experimental from here as 2. And you could swap them. It doesn't matter. You just have to keep the row consistent. If the row is 1, then it has to be as 1 again. And the nice thing about doing the logs is if you end up with a negative value, everything will work out in the wash. If they're consistent. And you could end up with a -1 though. Okay, now you could do this without doing the equation, but it's a little trickier now, at least for me, to recognize why that's a 2, because now we're tripling the concentration, not doubling like I showed in that previous slide. Now we're tripling. So if we tripled the concentration of ClO2 and the rate went up 9-fold, what's M have to be? 2. If we triple the concentration and the rate went up 3-fold, well, that's an N. What does N have to be? 3 to the what equals 3? 1. I know that this part's confusing because I've seen this before, right? Ask, what questions do you have? Where are we confused? Yeah. Same equation for n. Yep. Do you guys like the equation? Or do you like looking at the data? Equation? Either way, and I think as you practice the problems, when you can start to recognize what the concentration's happening and what's going on with the rate, it becomes easier. But I like the practice that you get with the equation because you don't have to guess and check basically. Let's write this out here. We can write our rate law now for this particular reaction. Rate equals K times the concentration of ClO2 squared times the concentration of OH minus raised to the power of 1. Okay? So M was 2, N is 1. Okay, so that's our rate law. Oftentimes this is what we're looking for. We can also solve for the rate constant, and we're going to do that on the next example. Are there questions on this one? Go back. Yeah. Okay. So let's write this out. So this is a different problem. So here we have a reaction of NO plus H2 forming N2 and H2O, and we do have some stoichiometry here, okay? So let's determine the rate law expression first, and then from that, we're going to determine the rate constant K. All right. I'm going to let you all work on this one for a couple minutes, and then we will work on it together. Feel free to work with your neighbors. first thing, which two experiments are you going to use to find the order with respect to NO? Which ones? Find the order with respect to NO. 1 and 3? Yeah, 1 and 3. Okay, so we're choosing those because the rate is, or excuse me, the concentration is changing for NO, but it is constant for H2. Okay? So then to find the order with respect to H2, we're going to use 1 and 2. And again, the concentration is changing in H2, but the order is, oh my goodness, but the concentration is constant for NO. That make sense? Okay, cool. How many people used an equation? Okay, how many people did not use an equation? About half and half. Okay, cool. I'll show both for one of these, and then we'll just give you the order for the other one. So let's find the order with respect to NO. So we're going to use experiments 1 and 3. We know that for 1 and 3, the concentration of NO is doubled. And what happens to the initial rate? Goes up by a factor of 4, right? My math right? Yeah. So the order has to be 2. Okay. If we want to use the equation, M equals log rate 1 over rate 2. Something like that. Is that correct? Yep. Yeah. So if I'm looking at comparing these two rates, initial rates, and if I divide this rate by this rate, I get a factor of 4. And it's a lot easier to see if they're doubled sometimes. So for instance, in 1 and 2, if you double 1.23, you get 2.46. But yeah, that's where that's coming from. Oh, no. For 1 and 3, it goes up by a factor of 4. Yeah. Okay. Good on the equation? Yes. For this? Under the M. Oh. That's going to be the order. So, and I think this is the technique you're both using, so that's where I'm doing it. So, the order is basically, we're saying we're doubling the concentration. That's where the 2 is coming from. The rate is quadrupled, but you have to find some power that will allow that to happen. Yep. Okay. And then for H2, we're going to find that H2, the order is 1, right? Yes. Okay. Again, just looking at this, we're doubling the rate, so doubling the concentration, the rate is doubling. we have to raise that to the power of 1. And if we want to write that out in terms of our powers, 2 raised to the 1 is 2, so n equals 1. You could also do the big equation for that. Choose your favorite, but again, you won't get that equation on the exam, so that if you want to use that, you have to memorize that one. Okay? But now we need to find our rate constant k. All right. We know this equation, rate equals k, concentration of NO squared times the concentration of H2. Okay, we figured out those orders. We know M and N, or whatever we want to call them. So the way we can calculate K is by taking one row of experimental data and plugging that into the rate constant, to the rate law. Okay. So what we can do is our rate is essentially our rate is equal to our initial rate. So if we pick experiment 1, the rate is going to be 1.23 times 10 to the minus 3 equals the concentration of NO, which is 0.1. Again, I'm just pulling from this first row of data. We've got to square that times the concentration of H2, which is 0.1. Everyone okay with that? Oh, I'm not. Now are we okay with that? Okay. So we can solve for K. And we should end up with K equals 1.23. But we need units, okay? Units are less fun in this section of material. But, and it's because we've got different orders with respect to reactants. So for instance, when we solved for K, I'm going to rearrange this rate expression, okay? We're going to have rate, which is given according to our table in, that looks funny. Oh, no. Yes, no, it's fine. Moles per liter per second. Like that. And we're dividing by the concentration of NO squared, and that's in moles per liter. And then the other one is moles per liter. Okay, so let me back up. I'm taking this equation, rearranging to solve for K. So I'm dividing both sides by the concentration part to get this. Is that all right? Everyone okay with that? Okay. And again, my units, rate is given in moles per liter per second. Concentration of NO is moles per liter squared because we have to square it, so that squares the unit as well. And here we have moles per liter. So now we have moles per liter per second divided by moles per liter cubed. But we can cancel out this moles per liter with this moles per liter, and we end up with 1 over second over, these are ugly, that, which gets a little bit better. We can do liters squared over moles squared times seconds. And I'm doing some of the math there, that algebra that everyone loves. Yes?
So if the orders change, does that mean the units change
Exactly. If the orders change, the units change. And that's why they're less fun here. There's not just a consistent unit. But the units can be useful to help you figure out the order of a reaction, sometimes. Questions on that? Yes?
Is it acceptable to write big F to the negative 2, S to the negative 1?
Absolutely. Yeah. Yeah, this could also be m minus 2, s minus 1. Yeah. Liter squared is coming from the big M. Moles per liter squared. Oops, that was supposed to be the. Yeah, so it's all in there. That's why it is kind of nice to write capital M minus 2. Other questions? Okay. All right. So let's tie what we've just done in with what we did on Friday last week. So, yeah. So last time we were talking about rate of change with respect to time, and we were relating rates to the stoichiometric coefficients for a reaction, right? And we said something to the effect of, if you have reactants and you want to relate their rate, you have 1 over A times concentration, change in concentration of A over change in time equals, you guys remember this? And then you can relate it to products as well. Okay. Minus, yeah. So we can take what we've done with the rate law and relate that stoichiometrically to other reactants and products. So let's first determine, we can first determine our overall rate for a given initial concentration. And that's kind of done here for you. So it says describe the rate of change for every species when the initial rates are, the NO concentration is, initial concentrations are 0.25 molar for NO and 0.2 molar for H2. We've already calculated the rate constant. That's going to be the same. Okay? It doesn't matter which experiment you picked in that data table, you're going to calculate the same rate constant. Right? And so we can calculate just then plugging in our initial rates into our rate law expression and overall rate. Okay? And so I put in the 0.25, I put in the 0.2, we used our rate constant, and now we end up with a rate, 0.0154. What does that rate mean? What is that a rate for? I mean, we said overall rate, but we've talked last time about rates of reactants disappearing and rates of products disappearing. Can we relate that to any reactant or product? This part's tricky, okay? So this is, if we take a look at the stoichiometry, we have 2 NO, 2 H2, 1 N2, and 2 H2O. Our overall rate would be relatable to a reactant or product with a stoichiometric coefficient of 1. So in this case, that's N2. So N2 is being produced at a rate of change of N2 concentration, change of time, equal to this value we just calculated, or had calculated for us. And the reason being, it had a stoichiometric coefficient of 1. If none of the things had a stoichiometric coefficient of 1, you would have to divide by its stoichiometric coefficient. Okay, like this. Which is a hint for the next question. Okay, what H2O is being produced at what rate? So we know that H2O has a stoichiometric coefficient of 2 in this reaction. And so the rate, as we relate it to an overall rate for any other reactant or product, is equal to the change in the H2O concentration over time times 1/2. And I left it as a positive here because we're producing H2O. And so we can plug in the stoichiometric, or excuse me, we can plug in that overall rate, 1/2 of that value, to get the rate of appearance of H2O. We get, oh shit, I'm sorry. Nope, take that back. Erase it, everyone erase. Sorry. We're solving for H2O. There. We're multiplying by 2 to get that rate. So 1 N2 produce 2 H2O. Okay, you think about that logically, so the rate has to be doubled. Yeah? So what I ended up doing here is putting in this value, setting it equal to the rate is equal to 1/2 times this factor. Does that make sense? And we're solving for this, delta H2O over delta T. Sorry for being confusing there. So multiply both sides by 2. So delta H2O over delta T equals 0.0308 moles per liter per second. Everyone okay with that? Yeah, sorry. Yep. Yeah. Yes. Multiply by 2. I mean, if you want to go for it and just think like logically, this is a logic problem, right? Be careful, because we have to relate it to a reactant or a product, or an overall rate in this case. If there was a stoichiometric coefficient in front of the N2, we need to take that into effect. Other than one. So what is the rate that NO is being consumed? And you don't need to include the negative sign. Yeah, 0.0308. Same as the rate that H2O is being produced, and H2O is the same as, and H2 is the same as well. Okay, those stoichiometric coefficients are all 2. The rates of either disappearance or consumption and the rate of production of H2O, those are all going to be the same. Super thrilling. Okay. Couple things here. Large value of the rate constant means the reaction is fast. Small value, slow. You can determine the units for the rate constant. Once you know the rate law, like we just did, calculate those units, do that unit analysis. Everyone loves unit analysis. That's like what we do on the weekends. Sum of exponents gives overall reaction order. That can be useful as well. Okay. I want to do this one here real quick. we've experimentally determined, so someone's already run the experiments and did some stuff, and determined that the decomposition reaction for N2O5 is first order. Okay? So the rate law has to be rate equals K times N2O5. That's it. The reason I want to point this one out, see the stoichiometric coefficient of 2? That is not going into the rate law automatically. Okay? So we said that the overall order for this reaction is first order. There's only one reactant, so we know it has to be first order with respect to that reactant. So rate equals K times N2O5. But from last time, the concentration changes with respect to time according to rate equals minus 1/2 change in the N2O5 concentration over the change in time. This is where you use that stoichiometric coefficient. Easy place to see it confused here. And when to use the stoichiometric coefficient and when not. Yeah?
Why is it
It is negative because the concentration is decreasing for that reactant. In the last problem I said, what is the rate of consumption? We assumed, we report values as positive, rate values as positive, so I just said ignore the sign. But it is, when writing it like this, I tend to include the sign. Other questions? How do I know in the second part here that the concentration with respect to time, which equation I'm looking for? And it's basically just the wording. So concentration with respect to time, it's got to be this type of rate expression. Rate law has to have that rate constant in it. Is that helpful? It may be better to write out your you. No, absolutely not. Never. I don't know what they're gonna do. I know that they will get back to you. Okay. I'm just saying, make sure. Yeah, I estimated it correctly.
Yeah, I'll email this. Thank you.
Well, maybe. It's not organized well, but this is 11.
Okay.
No, I misnumbered. Here you are. It's
Okay. Thank you.
We're good to blank.
All right.
Yeah. Yeah. So one more question, y'all.